All right, everybody. Well, welcome everybody to today's webinar, a tour of NASA's Antarctic Meteorite Lab and Astromaterials3D. My name is Paige Graff, and I'm the lead facilitator for today's program, but we'll introduce a number of other folks that are on the line with us, ensuring that you can all enjoy what we have to share with you today. We're basically broadcasting from the NASA Johnson Space Center in Houston, Texas. Some of us are still working from home. Some of us are in our offices there at the Johnson Space Center, but we're all here for all of you. So we want to welcome all of our participants from 33 different states across the nation, as well as Puerto Rico, Canada, Finland, Indonesia, India, Nigeria, the Philippines, and Switzerland. So we have a worldwide audience with us here today. We want to welcome all of you, including our community college students, university students, interns, educators and students in grades 4 through 12 plus, informal educators with libraries and museums and solar system ambassadors. We've got a large array of individuals joining us today, and we really welcome and are so glad all of you are with us today. Now, I also would like to send out a special thank you to our Infiniscope partners at Arizona State University for hosting this webinar. These folks at ASU are absolutely fabulous partners with resources of their own that you may want to check out at infiniscope.org. As a matter of fact, one of our tours today, our virtual tour today, is utilizing one of the assets from Arizona State University and their Infiniscope program. And so we are so thankful for them and appreciate us being able to have this webinar hosted through their YouTube channel and, of course, through Zoom webinar. We also really want to thank our featured speakers and our event facilitators. Kellye, Pando, and Erika Blumenfeld. These folks are very, very busy working in a lab as well as working on Astromaterials3D. We are so lucky that we have them today to share the work that they do on a daily basis. But also folks like Roger and Kim and Suzanne and Rosina, and I believe we have another individual, Cecilia, joining us, helping to monitor questions you may have during today's session. So we are thankful for all of our speakers. All of us are basically part of the NASA Johnson Space Center Astromaterials team. Now, the one other thing that I'll mention is that starting in 2022, we're going to host a few more types of events, especially for upper grades. High school especially, and also college level students. And those webinars will be about career paths to NASA, where we can highlight how an individual actually made it to what they're doing today and a little bit about what they do, so that folks out there have a little bit of insight into how you too might be able to end up on a career path to a NASA site or to NASA research. So those things will be coming in 2022, but for today, we want to focus on our Astromaterials, Antarctic Meteorite Lab, and Astromaterials3D. So with that, I'm going to stop sharing my screen, and I'm going to turn things over to Kellye, who'll introduce herself very briefly and give you a tour of our Meteorite Lab. So Kellye, thanks so much for joining us. Over to you.
Good morning, everybody. Like Paige said, my name is Kellye Pando. I work in the Meteorite Processing Lab. Let me share my screen. Forgot to do that. All right, so I work in the Meteorite Processing Lab at Johnson Space Center. Just a quick little background on myself. I got my bachelor's degree in geology in 2007. After that, after I graduated, I participated in an internship with the Lunar and Planetary Institute, and I got to work in one of the planetary research labs here at Johnson Space Center. And there I got to do some research understanding how planets formed And then after I did that, I was able to get a full-time position with Aries working in that same lab. And then a few years later, I decided that I wanted to try something different. So I moved over into the curation department, and now I am in the meteorite processing lab. And that's where I am today. So what we do in the lab that I'm going to show you, we work with meteorites, which simply stated, meteorites are rocks from space. There are a lot of different kinds of asteroids and meteoroids that are out in our solar system, and pieces of those and pieces of other planetary bodies sometimes find themselves on a path that collides with our planet. And so a rock in space can travel through our atmosphere as a meteor. If you are looking up at the sky and you see what a lot of people call a shooting star, that's actually a meteor. It's a rock that's traveling through our atmosphere really quickly. It gets really hot. So you can see it burning in the sky. And then once it hits the surface of the Earth, it's called a meteorite. And that's what we have in our lab. So all of the meteorites in our collection are found in Antarctica. So we partner with the National Science Foundation, who provides funding and logistics to send a team of people to Antarctica every year. It's a group of about 6 to 8 people. This group is called ANSMET, and that stands for the Antarctic Search for Meteorites. They travel across the ice and looking for and collecting meteorites. If you can see in this bottom left picture here, they're picking up a big meteorite off of the ice there with some tongs. Then they package all the meteorites. Each one gets stuck in a Teflon bag and packaged up and put inside these big coolers to keep them frozen. And then they get shipped back to us here in Houston, where we get to store them and process them and get them ready for people to do research on them. One more quick thing about ANSMET. So this is the Antarctic continent, and this little yellow rectangle is represented here on the right. And each of these little blue triangles is specific locations along the trans-Antarctic mountains, where the ANSMET team, they visit these various locations each year to look for meteorites. So that's where our meteorites come from. So this is the door leading into our lab. So let's go ahead and go on into the lab. We are a class 10,000 clean lab, which means we cannot have more than 10,000 particles per cubic foot in the air in the lab. So in order to try to mitigate having particles in the lab, we have to cover up our clothes and ourselves so that we can go into the lab covered, so we're not dropping off little bits of things into the lab. So we have this room, this is called the gowning room. We've got multiple shelves of gowns and caps and things that people can put on. Here's a quick picture just to see. So you have to wear a cap that covers your hair. You have to wear a smock that covers up most of your clothing. And then we have these blue booties that cover our shoes. And then once we get into the lab, we also wear gloves and things when we're handling the samples so that we don't contaminate anything. So we put on a smock, we get covered up and dressed. I'm gonna spin you guys around a little bit here. Hope I don't make you seasick. To the door on the other end of the lab. So I have a question for you guys. After we get all dressed up, but before we actually go into the lab, we have to go through what's called an air shower. So you guys can put your answers into the chat, what you think an air shower does and how does it work?
Excellent. So for those of you watching the live stream, think about this answer to yourselves or discuss it with others. For those of you on the webinar, if you put in your school or org name and then give us your answer, we'll read off some of what you think how an air shower works. So I'm going to give it a couple of minutes and then I'm going to read a few answers out loud. So standing by. Boy, we've got some answers coming in. Downs Elementary says blows air rather than blowing out water like a real shower. Someone else has mentioned that it blows off any loose particles and maybe sucks them up. The Houston Astronomical Society is mentioning that it cleans off dust and etc. that may be on an individual. Parkview Middle School is saying maybe it sort of rinses off particles. San Benito High School says a blast of air sweeps away any remnants. Now, our Southwest Community College says a high pressure air blows those particles away and off a person. We have another solar system ambassador from Florida that says it's a directed airflow, he thinks, that is intended to blow off any particles from any parts that you might have on your body. And AX Benavides from Brownsville, Texas says blows particles off of you. And TISD says, we think it takes all your dirt off of you. So some good answers in there, Kellye, coming in. How does this air shower work? And I noticed the door's open. Is that a part of it?
Yeah, so those answers are all great and pretty much true. So what it is, this door that you can see open sort of on the right side of the picture, we have to close that door. So we're all closed into this tiny little space. And we push this button and air is blown out of all of these little nozzles, and it blows in sort of a generally downward direction. It's pretty windy in there when it turns on. So it's blowing, and it does blow the particles, any excess little dirt or fabric particles, pet hair, whatever you might be bringing into the lab with you. And then this, where I'm standing here, this is kind of a grate, and then there's an empty space underneath with vents. So that air, as it blows down over us, the stuff goes down below us and out through some vents so that we don't bring it into the lab. So good job. All right, so once we're all gowned up and blown off, we can actually go into the lab. So this is the main room of our lab. We actually have 3 different rooms that we sort of move about in as we work. In here, you'll notice a lot of stainless steel metal stuff. That's because stainless steel is one of our approved materials for coming into contact with the samples. Over here, you'll see a freezer. So we have actually 3 freezers. And so when the samples come back from Antarctica, like I mentioned, they're still frozen, and we keep them in this freezer until we're ready to actually process them. Each sample is wrapped up in its own Teflon bag with Teflon tape, and then they stick a bunch of those in these slightly larger bags just to kind of help keep things from getting lost or tossed around. So we can put samples inside here. This is one of our glove boxes. All of our glove boxes or glove cabinets, these are fed with nitrogen gas. There's a constant flow of nitrogen gas, and that helps us to keep our samples dry and in an environment that is non-reactive. And we put them inside this cabinet to thaw. I'll show you really quickly. Inside, this is a view inside the cabinet with some samples that are sitting out, thawing and drying out. And so you can also see in this lab, we have, this is Kevin. He's actually our curator. He's sitting at one of our flow benches. So the way a flow bench works is air is pulled in from the bottom, and then it blows out across, there's a big vent back here that it blows out. Basically, it's blowing towards you. And this is to help keep any extra particles from floating onto the meteorites. We are worried about protecting the meteorites from us. We're not worried about protecting ourselves from the meteorites. So once we, let me pop you guys into this room back here. This is where we have most of our storage. So we have all of these desiccator cabinets. Again, they're all fed with nitrogen gas. And then inside of them are these little metal trays that we can put samples into these trays. So these are full of meteorites that have been processed and are being stored. Again, we have a couple more freezers in here. And so we have lots of storage space, although the more meteorites we bring back, the more storage space we need. So, so let's come back in here. So the first thing we have to do once we've thawed those meteorites is to do what's called initial processing. So I'm going to take you guys to our 3rd room. In here we have another flow bench. We have some storage for some tools. This is a big bandsaw cabinet. I'll talk to you guys about that in just a minute. And so when we do initial processing, like I said, we only have certain materials that can come into contact with the meteorites. Stainless steel, aluminum, and Teflon are our only approved materials that can touch the meteorites. So we have to use stainless steel rock splitters to break the meteorites open. We have hammers and chisels and chipping bowls, tweezers. We even have dustpans and little Teflon brushes to sweep up any little debris that comes off when you're breaking rocks open. We have Teflon bags and tape. We've got aluminum containers and stainless steel containers, whatever we need to be able to handle a rock or store a rock. We've got all the correct materials to use for that kind of stuff. Initial processing, I'm going to come back to this, but first I want to talk about initial processing. So what all of that involves. And what we do is we photograph each meteorite. We take several photographs of it, we weigh it, we write a physical description of it, the color, the texture, do we see inclusions or chondrules, anything like that. Then we break the rock open, we take more pictures of the inside and write more descriptions about that. And then we will take this one little chip that we will break off of each rock and we will send it to the Smithsonian Institute in Washington, D.C. And what they do there is they make something called a thin section, which is a slice of the rock that is thin enough for light to pass through it. And then what they do is they can use special microscopes and microprobes to look at that thin slice, and they can classify the meteorite and they can determine, you know, is it an H5 chondrite or an aubrite or something else. Another way we can process meteorites is using this. This is our bandsaw cabinet. And again, it's all fed with nitrogen. And here's a quick peek of what it looks like when we're using the bandsaw cabinet. You can see the glove ports here. And what we do is we take a meteorite, we mount it onto this stage here that moves back and forth. And then the bandsaw blade is here and it's stationary, and you just push the meteorite through so that it can cut off a slab of that rock. And I'll go ahead and show you guys a little close up here. So you can see the bandsaw blade is cutting through cutting the slab off, and the rock is held in place by all these little Teflon wedges and these little dome pieces and these stainless steel screws that we use to kind of try to hold the meteorite in place so it doesn't move while we're cutting it. And while we're while we're in this room, I'll give you guys a quick peek. This is our pride and joy. This is Big Lou. Big Lou lives in its own box fed with nitrogen. This is the largest meteorite that has ever been picked up by the ANSMET team in Antarctica. It's an ordinary chondrite. I'll go into that here in just a minute. It weighs about 240, 250 pounds. And it was picked up in 1985. So this is our big Lou, and you can see here how big it is compared to a person. We do not have any other meteorites that are even close to this big in our collection, but we do have some pretty big ones. Actually, if you can see down here underneath Big Lou is some of our bigger samples that we can't fit into any of the storage cabinets. Okay, let's go back into the main lab here. So I keep mentioning the word chondrites and chondrules. So ordinary chondrites are the most common type of meteorites. Probably about 85% of meteorites that are found on Earth are ordinary chondrites. The reason they're called chondrites is because they contain something called chondrules, and you can kind of see some of them in these pictures. There's a little one here, but really I'm pointing at this little one here and this one, but honestly, any of these round spherical shaped things are chondrules. So chondrules are basically silicate materials, so like olivine or pyroxene. And what happens is they get melted and they're cooled very quickly out in space. So they cool into these perfect little spheres. And then as those little pieces come together and they get incorporated into a larger piece, a larger rock. So these are lots of chondrules that are kind of stuck together by a matrix. They make these nice little meteoroids out in space that fall to Earth to be our meteorites that we study. And the reason that these chondrules are really cool is they contain some of the oldest materials that we have ever really been able to identify in our solar system. So based on that bit of information, can you guys think of why it's so important that we study meteorites? What would be the reason? Why are we going to all this trouble to pick these things up and get them ready and study them?
So a very important question for you to ponder. So for those of you on the live stream, or if you're watching the archive, think about this, the answer to this question. For those of you on the webinar, why is it that we study these meteorites? Why is it so important? And we'll see what types of answers come in the chat. So such an important question here. And Kellye, I'm going to read some of these answers out loud as we see some of them come in.
Okay.
So I'm seeing from San Benito High School, they're saying it's important so you can know what makes up our solar system from its time of formation. Downs Elementary says to know more about these rocks and to see if there's perhaps any signs of life from space. Someone else has said to better understand the formation of our solar system. Quaker Valley Middle School says to see connections to Earth and see back in time. One of our solar system ambassadors from South Carolina says to better understand the origin of life. Creekview High School says to learn about the formation of the solar system and all the planets. Now, our community college, Southwestern Community College, says to tell us about the age of the solar system and the early solar system. Mississippi State University, a solar system ambassador, says that that gives us a window to the original material from the solar system. Earth rocks have been processed tectonically and aren't as old as meteorites. And there's a number of other things in there. Oh, Parkview Middle School says, so we know what exists outside of our own Earth as we search for other materials in our solar system. So some pretty interesting answers there. What do you say, Kellye?
All of those are great answers and true. So I switched the picture here. So right here is another type of chondrite. These are carbonaceous chondrites. These are meteorites that contain fewer chondrules, but they still have some, but these have a lot of carbon and organic matter. So like amino acids and things like that. So yes, as far as understanding how life may have formed on this planet, carbonaceous chondrites can definitely help us sort of move in understanding how that may have happened. And yes, the ordinary chondrites, those chondrules are so important for understanding what our solar system was like before we formed into all of our planets. Which leading into that, as you may or may not know, so basically what happens is little particles come together and they make bigger and bigger objects. As those objects get bigger and bigger, they get hotter and hotter and they will completely melt. So when you're building a planet, it gets so hot that everything melts, and the heavier elements like iron and nickel, they'll sink to the center of that. And then the lighter elements like silicon and aluminum and sodium, they'll kind of float out towards the exterior. And so what you're left with is a metal core, a molten mantle, and a cool hardened crust, which is what our planet has. And so we actually do have some meteorites that come from things that are bigger, that are these bigger planetary bodies. So for instance, we have meteorites that we believe came from Vesta. Vesta is an asteroid, a really big asteroid that's hanging out in our solar system. It got pretty big, but not quite big enough to completely separate out into a core, a mantle, and a crust, but it kind of did some separating. So these meteorites we know came from something that was starting to separate out, didn't quite make it. So these are really great for understanding sort of the in-between steps of how you go from a chondritic type meteoroid to a more differentiated planet body. We also have meteorites that come from fully separated out planets. So these, we have been able to identify meteorites that came from the moon. So these are little pieces of the moon that got knocked off and floated around in space and landed on Earth. So we have an amorphosite breccia, basaltic breccias, and we were able to identify these based on data that was collected from the actual samples of the moon that were brought back by the Apollo astronauts. And by other rover data and things like that we've been able to collect from planetary bodies. So one last thing I'm going to talk to you guys about on that note is speaking of meteorites that come from other planetary bodies, This cabinet here is designated for processing meteorites that came from Mars. So this particular meteorite here, this is a really special Martian meteorite. It's actually really big, which is cool because we don't have very many Martian meteorites. I think in our entire collection, we have maybe 14 or 15 meteorites that we know came from Mars. But this one's really special. It was picked up in 1979. I'm going to show you another picture of it here really quickly. This is a slab of that rock that we cut using that bandsaw that I showed you guys. And it's inside of the Teflon bag. So it's not a great picture, but that's okay because you guys are going to see some better pictures in a minute. But you can see these really dark spots on the rock. So these are little, turns out, little glass inclusions. So little glass beads that got trapped inside the rocky matrix here. And in the 80s, they were able to open up these little glass inclusions, and there was gas inside of them, and they analyzed those gases that they found inside, and it turned out that they were a really close match to what the Martian atmosphere is made of. They did not match Earth's atmosphere, they matched Mars. So this was the first time that scientists said, oh my gosh, we have this meteorite and we know where it came from. We know for sure it came from Mars. So this was a big deal and it was really important. And you know, this is how we slowly we gather these meteorites and we can slowly learn where they come from and how they got here, and they can teach us a lot of things about the other planets in our solar system. So, like I mentioned, if you guys want to see some much better pictures of these meteorites, this Martian one and some others, Erika is gonna give you guys a tour of Astromaterials3D. So I'm gonna stop sharing so that we can pass it along and you guys can listen to some really cool stuff that Erika has to show you guys.
Hi, everyone. Let me just get settled here. I'm excited to share with you the Astromaterials3D project. Again, my name is Erika Blumenfeld, and thank you, Kellye, for that amazing tour of the Meteorite Lab. Now I'm going to give you a tour of Astromaterials3D. And so I am a transdisciplinary artist and the science principal investigator and project lead for Astromaterials3D. I have a Bachelor's of Fine Art in Photography from Parsons School of Design and a Master's of Science in Heritage Conservation Science from University College London. And I've been a professional artist for more than 20 years and have a research-based artistic practice that crosses disciplines and focuses on the intersections of art and science and nature and culture. And much of my work investigates the stories of connection across the cosmos. So in 2013, I approached NASA to propose the Astromaterials3D project because I had this idea. Might it be possible to hold a rock in one's hand that tells the story of the whole cosmos? Although this is a poetic idea, NASA's Astromaterials collections tell this story, yet very few people have access to these incredible samples and the stories that they reveal to the scientists who study them. But what if you could have access to these rocks virtually? These questions led to years of development in order to make a 3D virtual model of NASA's space rock collections. How did we do it? Our interdisciplinary team uses 3 primary technologies. First, we use high-resolution precision photography, where in NASA's curation cleanroom facilities, I manually take around 240 photographs at angles across the entire rock using a high-resolution camera. Then we take these photographs into a structure from motion software and reconstructed using photogrammetric principles that are tailored to each rock's individual characteristics. At the same time, we scan each of the rock's interior using X-ray computed tomography, which gives us the data we need to create the one-to-one volumetric model of the original rock, as well as providing a preliminary view of what these rocks are made of. The mission of the Astromaterials3D project is to put NASA's rocks from space into the hands of researchers, educators, students, and the general public virtually in order to share their incredible stories through research-grade, information-rich, interactive visualizations. So let's head over to the website so I can show you. And so give me one quick sec. I'm going to stop sharing and pull up the website. Okay, hopefully you can all see. And okay, great. So welcome to Astromaterials3D, a virtual library for exploration and research of NASA's space rock collections. So in building this website, we wanted to create a visceral experience of where these rocks come from. And we have two collections currently on the site, the Apollo Lunar Collection and the Antarctic Meteorite Collection. So today we're going to focus on the Antarctic Meteorite Collection, but I hope that you'll come back and take a peek at the Apollo Lunar Collection when you have a chance. So let's head over to the Antarctic Meteorite Collection. And here you can see a view of our inner solar system. And as you mouse over each of the places where we have meteorites currently in the viewer, you can see where these incredible rocks come from. So let's head over to Mars, and I want to show you the sample that Kellye was just sharing with you, which is called EET 79001. We have two pieces of this rock, the large sample that Kellye shared with you, and we also have a smaller piece of this rock that I'm going to open in our Explorer application, which is a custom Explorer software that allows you to view this rock in 3D. And so I just wanted to show you some of what Kellye was sharing, where you can really hone in and view some of the dark clasts that she was talking about that are the glass spirals. Here's another one here. And you can also see the fusion crust, which was created when the stone flew through our atmosphere and met with extreme heat and pressure as it fell to Earth. So I want to give you a really great tour of the Explorer, but first I want to go back to the Explorer, to the main page, and pull up a different rock that we're going to look at. And that's GRO 17063. So here we are at the sample details page, which gives you an enormous amount of information about these samples. And we have two pieces of this rock, which I'm going to tell you about. And so I'm going to leave this page open for a minute. And I want to read to you the story for this rock, because it's an incredible story. So it'll take 3 minutes for me to read through this. And I'm going to leave this window open so you can just watch the rock rotate and experience a bit of this sample and its incredible story. So this is sort of the rock's biography, if you will. The distinctive story written in the cosmochemistry of meteorite GRO 17063 is waiting to be discovered. It was found in Antarctica by the ANSMET team during the 2017 expedition and is newly available for the research community for study. What we do know about this rock's story comes from its initial classification analysis, which found that it is a type of meteorite known as a CR2 chondrite, indicating that it is an ancient meteorite whose formation story is perhaps the most wondrous of all meteorites. This is because CR meteorites contain within them the oldest known material in our solar system, material that formed before our solar system even existed. Known as pre-solar grains, these microscopic interstellar dust particles were formed in the atmosphere of other stars. Pre-solar grains are the intact remnant material from older stars that survived the interstellar medium, survived the coalescing of the nebular cloud from which our solar system emerged, and survived the ignition of our own sun. These grains are older than 4.571 billion years. As a CR2 chondrite, this hand-sized space rock may also reveal new details that could help us expand our knowledge about the earliest processes that occurred in the protoplanetary disk. Chondrules, which Kellye was telling you about, and are the spheral-shaped droplets that accreted out of the solar nebula to form the first planetesimals, appear to be abundant in this rock. Chondrites preserve the precise evidence of the chemical and physical processes that were occurring as it formed, including temperature variation and the alteration from aqueous interaction. During initial classification analysis, calcium aluminum-rich inclusions, which are known as CAIs, were also discovered in this rock. CAIs are among the very first solids to form out of the nebular cloud that birthed our sun. CR2 chondrites are also known to have a wide range of diverse organic compounds, including amino acids and other prebiotic ingredients. With all the stories that this rock still holds within its composition, this remarkable meteorite could yet reveal new details about the pre-solar environment, the formation timeline and processes of the early solar system, and perhaps even new insight into the prebiotic material that contributed to the origin of life. So with that, let's open this sample in the Explorer application and take a look. So here you can zoom in with your mouse and see the incredible detail of the sample. You can move it around and see it from any angle. And so we're going to have a look at the console that you have with the Explorer application, which gives you the detailed information, threads back to the story that I just read you, and gives you the details about the processing, how many photographs we took for this model, how long it took for the SFM model to produce. In this case, it was 9 hours of the computer crunching on algorithms to create this 3D model. And then the X-ray computed tomography scans, which you can actually download for free here to look at yourself. And so let's take a look at that, the XCT information about this rock. So we're going to go ahead and slice, and you can use any one of these six slicing tools here to start to slice into the rock. And as I do so, you can see into the rock itself. And so I'm going to move over to this area here and slice a little bit further. And then I'm going to open up to questions. So let's take a look at this rock together. And you're looking at the interior of the rock here, although you can still see some of the exterior. And I'm going to go ahead and zoom in a lot farther. And so everybody in your groups, let's talk about what we see. So what do you see? And gather with your groups and put in the chat what you see. And in doing so, we are invoking our own artistic and scientific minds, and we're bringing our powers of observation to the table. What do you see as you look at this rock?
So in the chat, for those of you that are on the Zoom webinar, put in those observations that you're making of this sample. And if you're watching the live stream or watching the archive, think to yourself, what do you notice? What observations can you make? And any and all observations are good. And so we're going to take a peek at the chat, and Erika, I'll read some of the answers and acknowledge some of the folks that are putting in their observations of what it is that you're showing. So I'm seeing they're loving this whole idea of virtual geology. And Creekview High School says they see very circular, rather large crystals, perhaps indicative of slow cooling. Houston Astronomical Society says they notice chondrules. Southwest Community College says a bunch of chondrites in a matrix, maybe. One of our other folks says kind of perhaps looks like a conglomerate. Now give us your observations. What do you see which does lead into the interpretation? But those first observations, like someone has put in various shades of gray, it's really what we're noticing. Downs Elementary says many ovals and circles, a flat surface, as well as that rough surface on the exterior. Our EIE individual says air bubbles, they look like air bubbles that popped due to pressure. So they're giving a really interesting description. Another solar system ambassador from Indiana says they're noticing irregular shapes in what you're showing in this particular view. Wheat Ridge High School in Colorado says they can't wait to use this with their astronomy classes. So an observation about their future use of this. So some interesting observations as well as some interpretations. So Erika, can you give us a little bit more insight about your observations and what they may mean?
Yes, so those are all excellent observations, and what an incredible group of artistic and scientific interpretations that we have here amongst the groups. So you're all on the right track, and what we see here is are these tiny little circles. Some of them have even these white rims. And these are the chondrules that we have been talking about. And what's so exciting to me about this particular sample and being able to see into the sample is that you get to see actually this kind of feature where you can see the chondrule even on the outside of the rock and then see it interiorly. And if you zoom in even a little bit farther, you can start to even see the structure, the crystalline structure of this particular chondrule. So this is an exciting way to start to understand how to look at these samples. And I hope that you will come back to the site and explore all the samples that we have in the Astromaterials3D Explorer currently. I will let you know too, if you come back and you get stuck, we have a little tool here, which is basically a little tour. And so you can take the tour to get a sense of how to use this whole section. And that can help guide you as you learn about everything that we've included. So I'm going to close this sample out for now, and I'm going to head back over to the Antarctic Meteorite Collection homepage, and I'm going to go to another sample from Vesta. So Kellye also shared that Vesta is an asteroid, and we have a bunch of meteorites from the asteroid Vesta. And I'm going to open this sample, GRO 17049. And this would be the moment for anybody in the group that has your red, blue 3D glasses. I'm going to show you a really cool feature that we have in Astromaterials3D. So in the little view controls, you can go to this little icon here, which is our anaglyph 3D. And so if I turn that on and I close this, you should all be able to put on your glasses now. And I'm going to zoom in and start to give you a little tour in 3D anaglyph of the rock. And so you can see it's probably coming towards you. And again, if you don't have glasses today, don't worry. If you can borrow a pair of glasses or maybe get a pair of glasses from someone you know who might have one, you can always come back here to see this in 3D again. And every rock has this capability, so you can look at all of them. But for those of you who do have 3D glasses on, and actually even those of you who don't can see this, you're going to see these long striations, these long kind of lines across the surface as I move around. And so this is the fusion crust. This is the crust this is the part of the rock that as it was coming through the atmosphere was heated up, and there was an extreme amount of pressure as it was tumbling to Earth. And so these are called flow lines. These are lines that are created because of the process of it tumbling to Earth. Okay, well, so I want to just mention a couple of other things that you can do here. You can add pins. Here, I'm going to turn off 3D for a minute. You can add pins and share really cool features with your colleagues by adding different pins and then writing your comments here, and then you can save and share the link. And when you share the link, it will pull whoever you share it with exactly back to this with your comments in it. So that's a really cool feature. The other thing is that you can take pictures of the rock at any moment. If you like a particular view, you can just hit the pictures here, and you can share this page with your friends and your colleagues. So I'm going to head back over to the site for a minute. If you want more information about the project, we have an about page. We have a technology page, which you can explore. And we have frequently asked questions that might answer some of your questions that come up today. And then do have a look at the Teams page. There are an enormous number of people whose brilliant minds came together to help create this project. So I want to pause here, and I'm going to quickly jump back over to my my PowerPoint presentation so I can share one last thing with you. If you have your 3D glasses handy, you can you can put them back on, and I will leave you with this page of 6 other rocks that are in our collection that we've created anaglyph 3D models for. So you can get to see a few other samples in anaglyph 3D as we're wrapping up. And also there is the website address to find the Astromaterials 3D. It's just ares.jsc.nasa.gov/Astromaterials3D. And you can also just Google Astromaterials 3D and the website usually comes up there too. So thank you all for letting me share this project. I hope that you will indulge and explore these rocks that we have. We'll be launching there's 20 samples in the collection right now. We'll be launching another 20 samples in the next about 4 to 6 weeks, if not sooner. So keep an eye out for press releases and new samples in the viewer. So I'm going to hand back to Paige. Thank you so much.
Absolutely. And thank you both, Erika, as well as Kellye, for sharing not only where we process these meteorites that come in from Antarctica on an annual basis through the ANSMET expeditions, but also how we are able to take some of those meteorite samples and make them really, in a sense, accessible for others to be able to explore. So thank you so much for all of that information again, Kellye and Erika. And I think what we want to do, we do have quite a few questions that have come into the Q&A area. And as folks have more questions, we certainly want you to put them into the Q&A area so that we can make sure we answer as many as possible. So perhaps at this time, Erika and Kellye, if you want to stop sharing your screen, and if you want to share your videos, we can have folks sort of see you, and you can go back to any screens if you need to be able to share any other portion. Let's see if I can get myself. So hi, Kellye, and hi, Erika.
There.
And hi, everyone. We are so glad that we have some extra time for Q&A. And I know Roger and our folks, our facilitators, have been answering as many questions as possible in the Q&A, and they'll continue to do so as we grab some of these questions ourselves. So I'm going to start with Kellye, because a question came in when you were talking about the air shower. And let me see if I can re-find that question that folks were asking. Oh, it might have been actually answered, the air shower question. Oh, here it is from Downs Elementary. What does it feel like to go through the air shower? Is there a lot of pressure in the airflow? Is it a blast? Is it something gentler? How long does it last? Can you talk to any of that, Kellye?
So the air that comes through is just kind of room temperature air. And it comes out pretty quickly. So it's sort of like if you could stand in front of a really powerful fan for about 1 minute, it just kind of blows the air on you. So there's not a lot of pressure. It doesn't feel like anything too crazy, just like lots of really powerful fans blowing on you for about 1 minute.
Awesome. Oh, so for about a minute. And it is very much an interesting little process. And so going through an air shower, you think you take a shower every day? Well, every time Kellye or any of these folks go into the meteorite lab, they take an air shower. So that's kind of fun. Here's another question for you, Kellye. Somebody wanted to know, you talked about how meteorites are found along the base of the mountain range within Antarctica. Why, what is it about the base of this mountain range as opposed to just somewhere out in the middle of Antarctica? What makes that such a good area for searches?
So what happens is in Antarctica, there's a big ice, well, there's several big ice sheets, but there's a particular one on that side of the transantarctic mountains that ice sheet flows towards the mountains. And what happens is as meteorites fall and land on the ice sheet, they typically get buried in the ice, and then the ice sheet is slowly trucking toward the mountain. And when it hits that mountain and starts to sort of melt and ablate away from the wind, it uncovers those meteorites. So they tend to kind of pile up there. It's a long process. I think I saw an answer in the chat. Roger was mentioning that a lot of these meteorites are probably buried in that ice for thousands of years before they kind of get exposed and we can find them. So that's the main reason that we go there. There's just a lot of meteorites there, and there's sort of like this constant resupply. So we can go back to the same areas multiple years and still find new meteorites that maybe we didn't find before.
And we'll tell you, the folks that go to Antarctica each year, and I think it was last year that there was not a group that went. Is that correct, Kellye? Last year we did not send an expedition out?
We did not. Correct. They didn't send us an expedition in 2020, and they're not sending an expedition again in 2021 because of COVID. But we're hoping that we can send another group down in 2022.
Excellent. And we sure hope that that's the case, because it is certainly a fun expedition for all of those involved. And unfortunately, COVID has caused a little bit of a stoppage in being able to send folks out there. And speaking of COVID, somebody had a question, and I'm looking for it, about, even in the lab, even pre-COVID, is it not necessary to wear a mask? Is that not something in the requirements of your clean room lab there at the NASA Johnson Space Center, that masks aren't something that need to be worn?
So in the meteorite lab, we don't have to wear masks. Most of our samples, because of that flow bench that we do the processing on that's blowing towards us, or we're processing them in a cabinet. So our possibility of our breath contaminating the samples is a much lower concern. Also, these meteorites, I mean, we do everything we can to keep them as pristine as possible, but they have been sitting outside for thousands, if not millions of years, waiting for someone to find them. So they are somewhat contaminated in that manner, but we just try to slow down that contamination. But yeah, we aren't that concerned about covering, we don't really breathe on the samples as much as you might think. We do have clean labs in our facilities though, that handle extremely small particles, and they do have to wear face masks because they don't want to accidentally blow a particle away because they handle such tiny particles. But yeah, in the meteorite lab, we have a little bit more freedom in that respect.
And it's interesting that you mentioned that, Kellye, because for folks out there that may not be aware, we do at the NASA Johnson Space Center within the Astromaterials Research and Exploration Science Division, we house and curate all of NASA's extraterrestrial samples. So the moon rocks, like Erika mentioned, the meteorites, we have stardust particles from a comet, we have solar wind that was collected from a mission that visited a point near the L1 point between the Earth and the Sun. We have particles from comets and asteroids. So we have a wide variety of labs, and we'll have particles from asteroid Bennu coming soon as well. So a lot of different labs with a lot of different requirements. Now, here's a question for you, Erika. One of our participants noticed in a picture that it looked like there's a window between the camera and the meteorite you're photographing. Is that part of your practice, or why is there a window? Does the window compromise the quality of the picture? Any information you can share there? And you're muted, right?
I just realized I was muted. Yeah, thank you. That's a great question. So because the meteorites and all the samples that we work with need to be inside of nitrogen cabinets so that they stay protected, I have to also photograph them through the windows of their nitrogen cabinets. So that window that you saw is off one of the sides of the cabinet in what's called the SO port, or the science observation port. So the glass there is a higher quality glass that's optically clearer than maybe say the glass on the side of the cabinet, and that's so that we can do higher resolution science observations and imaging observations outside those ports. So it does impact the imagery, but we calibrate the cameras and the imagery with that in mind. So it becomes part of the process.
And it's amazing to think, Erika, how many actual images you get of every individual meteorite or lunar sample, because since we have lunar samples as well, that's pretty incredible. So for those of you out there that might think, well, I like science, but, I'm not sure if I want a career in science, this photography and art aspect that Erika has talked about and showed, you can really see that bridge of art and science and all that you can do with that. And it really opens up your eyes to new observations or new things you would perhaps have never thought about prior to thinking about making observations in a different way. And so, you know, art and science are such a powerful thing to be able to merge together and be an inspiration for the sciences. Now, as we are at the top of the hour, we still have questions that are that I have. So I think we have about 15 more minutes or so where we can get some more questions answered. But for those of you that might have to depart, by all means, Suzanne has put a SurveyMonkey link into the chat so that you can give us your input and feedback and or any additional questions you have on our event today. And I will be sending out a follow-up email with information about internships, links to these websites, as well as hopefully I'll curate all the questions that were answered during the session from our other facilitators like Roger or Kim or Cecilia and Suzanne and Rosina. So we appreciate all of the folks that have been on the line today, from our team at the Astromaterials Research and Exploration Science Division, and all of you from all around the United States and beyond. So if you have to depart, thanks so much. And we'll continue and get back to some additional Q&A. So as we do that, this question is actually for Erika and or Kellye. And this might be a tough one. Within these meteorites, and especially Erika, where you can see inside these meteorites, are there materials that have not been identified or can't be identified or are not well understood? Can either of you talk to that, perhaps starting with Erika, maybe?
Sure. Yes. I mean, I think how I would answer that question is from the standpoint of the fact that these samples are continuously coming into the lab. So the exploration of meteorites in Antarctica is something, you know, COVID aside, has been something that's been going on every year since the 70s. And so this collecting of meteorites always brings in samples that have new and unexplored possibilities. And that's what's so exciting, particularly like the sample that I shared with you, GRO 17063, that I read you that story about. What's so exciting about this science is that it's continuously growing. And you know, for samples that haven't been well studied yet, there's always that potential to find the unknown or the not yet seen. And I think that's what makes the science so invigorating. But I'll hand it over to Kellye. What do you think?
So they do find minerals. Very occasionally, minerals have been found in meteorites that we have not found on Earth. That doesn't mean they don't exist on Earth. They might just be really rare and we just haven't found them yet, or maybe they do only exist in that meteorite. But the thing about meteorites that's really interesting, that most of the things that we find in there are things that do exist on our planet. And that's because if you could take our entire solar system and put it in a blender and then take it out, you would basically have an ordinary chondrite. So it's all of these meteorites and things that are in our solar system are made up of the same thing that we are made up of. So it's just that, you know, it has it, like someone mentioned about the Earth, there's tectonic activity and things like that that sort of recycle our rocks. So we lose a lot of that historical information that these meteorites can hold on to for us. So, but yes, we do occasionally find minerals and things that we haven't discovered on Earth as of yet. But yeah.
And it's interesting, I'll add to that, because we have one of our scientists who is our Stardust curator, Michael Zielinski. And, you know, we've been talking about Antarctic meteorites, but meteorites fall all around the world, in the oceans, in Africa, in Arizona, in pretty much anywhere. But Antarctica is a place where some of our expeditions take place because it's one of many places to search for meteorites. but Mike Zielinski had recently gotten a mineral, Zielinskiite, and I might be mispronouncing that, named after him. It was a new mineral that I believe was discovered in a meteorite found elsewhere, not in Antarctica, but somewhere else. And so this new mineral was named in part after Mike Zielinski for all the work that he's done on meteorites. So there's definitely new minerals found, and the names of some of those minerals have a nice story attached to perhaps individuals pertinent to meteorite research. And the other thing I'll mention that Erika, as she was zooming in to that part of that GRO sample, and you could see the chondrules. I don't know if some of you noticed, some of those round circular objects had a bright ring around them. Some of them may have had a speckled ring around them. And the intricacies about what does all of that mean is not 100% understood. So there's always, and that's the beauty too of science, the more you investigate and observe, the more questions you have to research. So science is ongoing, and maybe some of you students out there will sometime work with meteorites yourself. So great question and great responses. Thank you, Erika and Kellye. So here's another question kind of related to meteorites. How do you know if the meteorite is from Mars or if a meteorite is from Vesta? How are those determinations made, and are they done right there in the lab where you work, Kellye, or somewhere else?
Okay, well, first I'll say that no, we don't do much as far as researching the samples go in our lab. Our lab is dedicated to curating and processing the samples and sending out samples to scientists and researchers who actually do that kind of research. But I will say the reason that we are able to know that different meteorites come from different planetary bodies is, well, there's a number of reasons. Particularly samples that come from larger planetary bodies, they are called achondrites, which means they don't contain chondrules. So we know they came from something big enough to have separated out, at least partially, those heavier metals into a core-like separation. We can do studies, particularly like for the Martian one, that the little glass inclusions that had gases trapped in them, those gases matched Mars's atmospheric data that we had collected from the Viking lander in 1976, I do believe. So we were able to compare that. So we knew, oh, this matches here. So we make the assumption that that's where it comes from. You can also do identification of minerals in the rocks. And I do believe like Mars rocks tend to have I believe they have more sulfur. They're more sulfur rich than most Earth rocks. So that's one way we can kind of know that, oh, this is maybe not normal to us. Just the abundance of different elements and minerals is different on different planetary bodies. Most of the information we have, lunar rocks, we have rocks from the moon that we can study. So those are really easy. Martian rocks, we don't have rocks from Mars, except for the meteorites that came to us. But we do have rovers on Mars and all kinds of other spacecraft that orbit the planet that can collect all kinds of data about the mineralogy and the petrology and all of the different things that that planet's made up of. For our carbonaceous stuff, like Paige had mentioned, we've got things collecting from Ryugu and Itokawa from like the OSIRIS-REx missions and the Hayabusa missions. So they're bringing back samples that we can get clear data on, that we can compare to the samples in our collection to see if we can figure out where those come from. So a lot of unmanned spacecraft help us with a lot of our identification of where meteorites originate.
And that's an awesome question and a great answer, because those assets there in space and the samples that we can actually study in laboratories, all of that information really helps build the story. And speaking of stories, Erika read you a story. Those stories come from the remote sensing data and the data from labs and things to be able to piece together that story. and to better understand the history and evolution of our solar system. So science from so many different angles brings together such a powerful sense of understanding. And our folks like to say, and perhaps Erika and the Kellye have heard this before, our samples, they're the gift that keeps on giving, because you can study so many parts of these samples and investigate them in so many different ways. So, so that's fabulous. So here's a question. I'm going to go to Erika first. With this whole idea of art and science and your background, what has been sort of the most rewarding aspect of the work that you have done, especially with regards to Astromaterials3D, and any advice you'd have for emerging scientists out there?
Wow, that's an excellent question. Thank you for asking that question. Let's see. You know, as an artist, to be totally honest, it wasn't clear to me that I would ever have an opportunity to collaborate in this way and produce an enormous project like this with NASA. And so for me, coming in and wanting to kind of trouble the lines between art and science, because I think a lot of the divisions of these disciplines, I think, are sort of arbitrary, and there's a lot that's shared across art and science. And for example, I always like to think of, you know, the wonder and awe of our universe is really where art and science meet, and we're both are collectors of questions and observations. And so for me, really, the biggest reward has been that the project is seen as valuable by the research community and by the agency and by the department that I work with, to the point that now the project is growing and will continue to grow, so that we will begin working with future missions and the samples that they're bringing back, and developing new capabilities so that we can continue to bring you samples that you can interact with. And then in terms of reaching out, you know, to the artists and the scientists in this group, I think it's really about allowing for your imagination, and following those impulses of your imagination to the places they lead you, and knowing that that journey is going to be exceptional and rewarding wherever it takes you, whether it takes you to the sciences or maybe to the arts or some other discipline to explore our incredible world. Thank you.
Awesome. And following that passion, I think, is just so important, because if you do what you love every day, and we've said this before, if you do what you love every day, you'll never work a day in your life. And to be able to have that type of experience and enjoy it and make those new discoveries and almost continue to be inspired by what you see in the world around you is a very powerful thing. So thank you for sharing that, Erika. And Kellye, we're going to ask you that same sort of question. What inspires you? What do you love about the work that you do? And what messages do you have for emerging scientists, both those in the elementary grade levels or those who are currently college students? What do you have to say for them?
So, I mean, I would say I've always kind of had an affinity for science. I like to understand how the things that are around me function and how they work. So one of the things that I find most rewarding in my position is that I get to handle rocks that are so incredibly old and represent so much important information about understanding where we come from and why we're here. And to be able to contribute to the scientific research in a way of being able to, you know, process the samples and allocate them out to scientists who can do really amazing research and find really amazing information from these samples that we send them. I feel like I'm really contributing to something important. And really, I guess my message would be, try everything. When I started in school, I started in college, I wanted to go into biology, I wanted to do forensics, and then I sort of stumbled into geology, and I loved it. And I still love biology, but you just try everything, see what you like, see what you don't like. There were things that I did in school that I just was like, oh, I can't do this. So, there's that. And that's one of the things about the internships that Paige mentioned in the beginning. Those are excellent opportunities for you to try something out. And I can't tell you how valuable it is to be able to do that and realize, oh, this isn't what I want to do, or, oh, this is exactly what I want to do. And to kind of get your foot in the door and experience as much as you can before, you can continue to change and evolve throughout your life. So, don't think you have to do this one thing, just try everything, go for it. And like Paige says, do what you enjoy, study a field that you actually enjoy. That's why I went to school for a science degree. I wanted to do science, and I'm so happy that I'm here now.
Awesome. Well, thank you both, Erika and Kellye. And we are at about 15 minutes past the top of the hour. And I think both their messages to everyone out there is so important. Explore everything, look at those internships, because if you find that you either love something or don't love it as much as you thought you might have, and then you can make decisions based on those things. And whether it's the arts, the sciences, biology, geology, or a mesh of the two or all of those things, finding what works best for you will give you that successful career at whatever level you're in or whatever type of investigation you're doing. So with that, again, being respectful of everyone's times, because boy, Kellye and Erika are so busy, right, Erika and Kellye? We're so glad that you were able to join us, Kellye and Erika, as well as our other folks that have been helping answer questions: Roger Harrington, Cecilia, Kim, Suzanne, Rosina. We thank all of those folks for being with us today. A special thanks to our Infiniscope partners and Sina Kirk. We are so thankful for allowing you to host this webinar through your venue and then share it through your live stream. And to all the folks that joined us either live or with the archive, thanks so much for spending some time with us. We hope you enjoyed and learned something today, and we hope you're inspired to go investigate and learn more about meteorites and all the other great stuff out there. So with that, we'll bring this to a close. Thank you again, Erika, Kellye, and everyone. Have a great rest of your day and a great holiday season.